Alright, so our first topic for this video is existence and uniqueness theorem. Existence, identified in N, existence, and uniqueness theorems. And this is for our weights, continuing on with where we left off last time. We want to show here that for each lambda in the dual of our Cartan subalgebra, there exists a unique isomorphism, irreducible, standard cyclic, L module of highest weight lambda, which may be infinite dimensional. Alright, theorem. Let V and W be standard cyclic modules of highest weight lambda. If V and W are irreducible, they are isomorphic, and this, of course, is going to be our uniqueness. We're going to set up a L module X to be the sum of V and W. If V plus and W plus are maximal vectors of weight, of course, lambda in V and W respectively, we can let X plus be their Cartesian pair in X. So X plus is a maximal vector of weight lambda. Let Y be the L submodule of X generated by our X plus, being standard cyclic, of course. And let P be a map from Y to V, and P prime be the map from Y to W, be the maps induced by projecting X onto its factors, of course. Thus, P and P prime are L module homomorphisms. L module homomorphisms. And since P of X plus is V plus, and likewise P prime of X plus is going to be W plus, we get that the image of P is V, and the image of P prime is W, not V prime. as irreducible quotients of the standard cyclic module Y. We have by our previous theorem, V and W are isomorphic. So that's uniqueness. It's based mostly on just what we've already done. The key in this case now is to getting existence to work. Because there's two different ways to approach it. I don't know if we're taking both or just one, but there's a fair bit of preamble here we're going to go through before we get to our existence theorem. So first off is an induced module construction. So we first observe, this is like some setup for it, motivation I guess, that a standard cyclic module has a B module, B being I believe the Borel of the base, contains a one-dimensional submodule spanned by a given maximal vector. So we begin our construction with a one-dimensional vector space d lambda with v plus as basis and define an action of B on d lambda by the action of H plus the sum of x alpha for positive roots alpha, so in our base on V plus is going to just be the action of H on V plus, which is going to be the action is going to be given by a character function for fixed lambda in H prime, which is going to make this d lambda a B module. As d lambda is just as well a module of the universal enveloping algebra of B. We can form z of lambda to be equal to the universal algebra of L, the tensor product over the universal algebra of B with d lambda, which is itself a universal L module under the natural left action of the universal algebra of L. Now we will see here that Z lambda is standard cyclic of weight lambda. First off, we notice that the tensor of 1 with v prime generates our Z lambda, obviously. And is non-zero. As we can think of UL as a UB module with a basis of 1 and the monomials of y beta 1 through y beta times through y beta m I m. Thus, 1 tensor v plus is a maximal vector of weight lambda, which we write as just v plus to keep things easy. From this we see that f for n minus being of course the union of the negative root spaces, then Z lambda as a un minus module is isomorphic to the universal algebra of n minus. We get that the universal algebra of L is isomorphic to the universal algebra of n minus, with tensored to the universal algebra of B by Poincaré-Berkhoff-Witt. So Z of lambda is isomorphic to U of n minus, then just tensored with the underlying field. We may construct Z lambda by generators and relations. I'm going to choose some non-zero elements x alpha in L alpha for positive roots. Roots are base. And we're going to let I lambda be the left ideal in the universal algebra of L, generated by all x alpha for alpha positive, along with all h alpha minus lambda h alpha acting on 1 for alpha being a root. These generators of I lambda annihilate the maximal vector v plus of Z lambda so I lambda also does. And there is a canonical homomorphism of left UL modules UL over I lambda into Z lambda, sending the coset of 1 onto the maximal vector V plus. Again, by the Poincare-Birkhoff-Witt generating the basis of U of L, we see this map sends cosets of the universal algebra of B onto F of V plus, so is 1 to 1. Thus, our Z lambda is actually isomorphic to UL over this ideal. Now there's a quick theorem before I move on to our next chapter. We're going to pick, let lambda be in H star. Then there exists an irreducible standard cyclic module V lambda of weight lambda. And the proof, you've already done most of the work for it here. Our Z lambda is standard cyclic of weight lambda with a unique maximal submodule y lambda. Therefore, V lambda as Z lambda over Y lambda is irreducible, and standard cyclic of weight lambda. And so then for our next two sections we're going to look at, first off, which of these V lambda are finite dimensional, and then for which V lambda, for finite dimensional V lambda, which weights occur and like what multiplicity they have, and that kind of thing, to get a better idea of their structure. So next chapter is going to be on finite dimensional modules, and our first topic in here is necessary conditions. Necessary condition for finite modules. suppose V is a finite dimensional irreducible L module. Then V has at least one maximal vector of uniquely determined weight lambda, and the submodule generates must be all of V by irreducibility. So V is isomorphic to V lambda. For each simple root AI alpha I, let Si, or alternatively S alpha I, be the corresponding copy. Yeah, corresponding is important in this one. Corresponding copy of SL2F in L. Then V lambda is a finite dimensional module for Si, and a maximal vector for L is a maximal vector for Si. Since there is a maximal vector of weight lambda, the weight for the Cartan subalgebra Hi in Si is completely determined by the scalar lambda of Hi, with of course Hi being H alpha I. This forces lambda of Hi to be a non-negative integer. And from that we get a theorem for free, which states that if V is a finite dimensional irreducible L module of highest weight lambda, then lambda of Hi is a non-negative integer. It follows from our previous results that if V is a finite dimensional L module with a weight mu Then we have that move hi is, of course, going to be the angle bracket of mu and alpha I in the integers. And so from this, the weights, and so this gives us a compatibility between the two different forms of weights we've been using so far, in terms of like the kind of abstract version we saw before, and this version we have them here, they're essentially the same thing. So everything we talked about weights before now kind of carries over. Okay, and recall that we called the highest weight lambda of v lambda is called dominant. To avoid ambiguity, we're going to let any element of h star to be called a weight whereas a linear function lambda with all lambda hi integral will be called, well, easily enough, it's going to be called integral. If all lambda hi are also non-negative integers, we call lambda dominant integral. Which gives us that the set capital lambda of all integral linear functions is thus a lattice in h star, or as we saw it before, as in the real Euclidean space generated by the roots. And this is going to include the root lattice. I have a hard time saying words. As before, the set of dominant integral linear functions is denoted with this plus, lambda plus. One last bit, if V is an L module, let lambda v denote the set of all its weights. For v being our v lambda, we can also write it as v lambda. And we have our existence. Let's look at sufficient condition for finite dimension. It comes with a theorem. Starts with a theorem, which will comes with corollary before we prove any of it. If lambda is a dominant integral, then the irreducible L module v as v lambda is finite dimensional, and its set of weights pi lambda is permuted by the Weyl group with the dimension of v mu being the dimension of v sigma mu for sigma in the Weyl group. And the immediate corollary is that the map from lambda to v lambda induces a one-to-one correspondence between our set of dominant integral linear functions and the isomorphism classes of finite dimensional irreducible L modules. And the corollary is immediate from the theorem, and the theorem is pretty immediate. Nope, it is not actually. There's a lemma inside the proof for the theorem. So we're going to fix standard generators xi and yi of L. And then we're going to work on a lemma real quick. So first off is that the bracket of the commutator of x and xj with yi to the k plus 1 equals 0. K is obviously non-negative when this is when I is not equal to j. B is that the bracket of hj on yi to the k plus 1 is minus k plus 1 times alpha I of hj times yi to the k plus 1. And lemma c, the action of x, xj I'm guessing on yi to the k plus 1 is negative k plus 1 times yi to the k times k on 1 minus hi. And the proof of this lemma, part A is just that alpha j minus alpha I, alpha j minus alpha I is not a root for j not equal to I. Part B is by induction on k. Things are happening. Induction on k. For k equals 0, then we just get that hj with y I is equal to negative alpha I of hj on yi. In general, the left-hand side equals hj yi k I to the k plus 1 minus yi to the k plus 1 hj, which we can start throwing around a copy of the yi. So we're going to strip, we get yik hj times yi minus y plus yi to the k hj, y to the I minus y to the I, h to the j, which is negative ki alpha I hj times y. We're going to split this up into yik, yi plus yik. We're going to go ahead and write this on a new line because we are out of room, as you do. Negative k alpha I of hj yi to the k times yi plus y to the I to the k of our negative alpha I of h of j times yi, which is something, which is negative k plus 1 times alpha I times hj times yi to the k plus 1 by the induction hypothesis. For part C of our lemma, I'm going to go ahead and write this up. I'm going to learn from my mistake with the last one. I'll write this on a new line. Xi times yi to the k plus 1. First off, we just split up this bracket into its commutator. Oops. K plus 1 xi, which is then the bracket of xi and yi on yik plus yi on the bracket of xi and yik, which is hi on yi to the k plus yi on xi times yi to the k, and use induction on k, and use part B. Now with this we can look at our proof of the theorem. So we want to show that the set of weights of V is permuted by the Weyl group, so it's going to make it finite. Now we're going to denote the representation of L on V by phi being a map from L to the general linear Lie algebra of V. Fix a maximal vector V plus of V of weight lambda and set, and then we're going to set mi to be lambda of hi with mi non-negative integers by assumption. Alright, so step 1. yi to the mi plus 1 on V plus is 0. So we're going to let W be our yi to the mi plus 1 on V plus by part A from lemma xj on W is 0 for j not equal to I, and by parts B and C we get that xi times yi to the mi plus 1 on Vi on V plus is yi to the mi plus 1 times xi on V plus minus our mi plus 1 yi to the mi V plus minus, I think this is supposed to be V plus mi equals 0. So xi on W is also 0. If W were non-zero, it would then be a maximal vector in V of weight lambda minus mi plus 1 alpha I, which is not lambda. Therefore, W is 0, and yeah. Part 2 is for each I, V contains a non-zero finite dimensional SI module. The subspace spanned by v plus yi on v plus through yi mi on v plus is stable, of course, under yi by the previous step. It is also stable under hi since each belongs to a weight space of V. So it is stable under the xi. Alright, step 3. That V is the sum of the finite dimensional SI submodules. Let V prime be the something, I'm sure. Sum of all such submodules which is going to be non-zero by step 2. Let W be any finite dimensional SI submodule of V. The span of all subspaces x alpha W for alpha in our root space is going to be finite dimensional, and it's also going to be SI stable. Thus, V prime is stable under L. So V prime is V, as V is irreducible. Number 4 is for each I. Phi of xi and phi of yi are locally nilpotent endomorphisms of V. If V is in V, then V lies in a finite sum of finite dimensional SI submodules and on such submodules phi of xi and phi of yi are nilpotent. Step 5, there's 9 total. Step 5's immediate says that SI is the exponent of phi of negative yi flanked by the exponents of phi of xi. Oops, and this needs to be an exponent too. Is a well-defined automorphism of phi. This is immediate, of course. Part 6. If mu is a weight, is a flattening of v, then Si of v mu is v of Si mu. Is v of the reflection relative to alpha I on mu. And v mu lies in a finite dimensional SI submodule v prime, and SI of v prime is the same as the previous automorphism of this form we saw. Previous such automorphism TAF, and so we essentially just copy that proof verbatim. Step 7 is that the set of weights is stable under the Weyl group, and the dimension of v mu is stable under reflection by the Weyl group. And since the Weyl group is generated by the reflections of the roots, we get this from 6. Part 8 says that mu of lambda is finite. From above, from the previous lemma, be a bit clearer. The set of a Weyl conjugates of dominant integral linear functions mu less than lambda is finite, and as we saw, contains mu lambda. Which brings us to our last step in our proof. The dimension of v is less than infinity, is finite. We know from a previous theorem that the dimension of v mu, the dimension of, I'll write that better, v mu is finite for all mu in our set of weights. And then it's just by chapter 8. And that'll be it, I guess, for this discussion. Next up, weight strings, weight diagrams, and generators and relations for this. And then maybe onto like multiplicity formulas. That kind of thing's coming up vaguely in the future, but Yeah, recording Pokemon right now is taking a long time. I know this is the place to talk about that, but so for the time being, I'm kind of cutting back a little bit, maybe potentially, because I kind of covered what I wanted here. Anyways, I want to keep going and get as much of this as I can. But for a couple days, we might only get 2 videos a day, as you do.